This screencast corresponds to Section 2 of your thermochemistry unit on enthalpy. And enthalpy is specifically the study of energy changes in reactions from reactants over to products. There's some terminology we need to know when discussing this. First of all, there's a thing called the system, and that's what we're most concerned with in thermochemistry, are the chemicals themselves. So that when I say the system is gaining or losing energy, I'm talking about the reactants and the products, the materials, the chemicals that are reacting. Okay. Then there's the surroundings, and the surroundings can be considered everything else. Anything in contact with the system is going to lose energy to the system if it's endothermic, and the reaction's gaining energy. So we need to know about the surroundings. And then don't worry so much about this. The universe is considered those two things combined. The system, which is doing the reacting, and the surroundings. So notice this diagram here. We consider the system are the things that are actually reacting, and I would not include the flask in that because the flask is not reacting, but I would definitely include the contents, so the things that are reacting. That's the system. And the surroundings is everything else. Again, I would say including the glass jar, the round bottom flask. Moving along, the way we measure heat change is called enthalpy. Enthalpy is symboled with the letter H. Conveniently, that lines up with something we think of as heat, as temperature change. And think about it, though, we can't really ever measure this quantity. We can't stick a thermometer into a chemical bond and see how much energy is stored there. We just can't physically do it. So what we have to do is measure the energy change across a reaction. So what we're really measuring is not the enthalpy stored in chemical bonds, but it's the energy change when reactants go through a reaction and turn to products. And we call that the enthalpy change. It can be absorbed, of course, if it's endothermic, or released if it's exothermic. So let's talk about those things a little bit. This is called an energy diagram. Now look at the blue line. The blue line symbolizes the energy content of the chemicals themselves, of the system, okay? And notice we're moving from reactants to products over time. So energy is your y-axis, time is your x-axis. Now, an endothermic reaction gains energy and it's stored in the chemical bond. So notice that the delta is positive. These materials have gained energy. If we're just talking about the system, it has gained energy. So there's a positive change in energy storage in the system. Exothermic is exactly the opposite, okay? Exothermic, from reactants to products, you lose energy. So energy is given off. The surroundings, including your hand, is going to feel hot if it's around an exothermic reaction. But the system, the chemicals themselves, have lost energy. So the sign for delta H is negative, and we're going to talk a lot more about that. Just remember, endothermic, the sign is positive because the system is gaining energy. Exothermic, the sign is negative. Okay, so the way we calculate the delta then is by doing a subtraction. We take the final, let's say, state of the system minus the initial. Okay, so let's go back to these energy diagrams. Notice the final, for an endothermic reaction, the final state is higher energy, and if we subtract the reactant's energy, which is a lower number, we're going to end up with a positive value. Okay, similarly for exothermic, the final state is lower. And we subtract that from subtract a higher number from that, you get a negative change, a drop in energy from in an exothermic change. So we always do it in this order. We take final state, energy content of the final state minus energy content of the initial state. But you guys know this better as products. Products are the final state and reactants are the initial state. So again, if the products have a higher energy than the reactant, it has gained energy. It's endothermic, so the value is positive. So it's really important to know the signs of delta H for endothermic or exothermic reactions, okay? In addition, you should know what the units are measured. The units of delta H of a reaction are kilojoules per mole, and usually it's per 1 mole of a reactant. And so that gets a little tricky if there's coefficients in front of the reactant in a chemical reaction. We'll get to that. All right, let's move on. So thermochemical equations is the way we're going to start formally writing chemical equations that are endothermic or exothermic, because we're going to now start including the heat term, but not just written as heat, heat lost on the right side of a reaction. We're going to actually write the number. The number of kilojoules is written in the reaction. So you'll have a number that appears in the balanced chemical equation. So here's the combustion of glucose, and glucose is a great fuel. We use it in our bodies to produce a lot of energy, and no surprise that combustion reaction, like all combustion reactions, is exothermic. The sign is negative because these chemicals are losing energy. I'm going to start writing that in the chemical equation as a number. So this could be plus 2,808 kilojoules. Okay, so the number given off is actually included in the equation now. Okay, now that can be written as per mole of, let's say, CO2 produced. And if I were going to write that number with per mole of CO2, notice there's 6 moles of CO2 in this reaction. So I'd take the number of kilojoules given off and I would divide by 6 if I need to represent this as per mole of CO2 produced. Okay, so be a little careful of your units. Okay, moving on, there's some different standard delta H's that we're going to look at, 3 in particular. And the first one is a molar enthalpy of solution. Most of the time when you dissolve a compound, ionic or polar covalent, there is an energy change associated with that. And it's positive or negative, so it can be exothermic, negative delta H of solution, energy is given off, or it can be endothermic as well. Okay, so let's look at a couple of examples that, in fact, you're familiar with. Most dissolution reactions are endothermic. It's going to take energy to break up molecules into ions or into smaller molecules. So that's going to take an energy added. So take a look. The delta H solution of this stuff, ammonium chloride, is positive. So note that, positive 15 kilojoules, meaning per mole, meaning that it is endothermic. And so we're going to write that term on the left side of the reaction. And this is something you're familiar with. You know, the emergency ice packs that you get on the athletics field if you turn your ankle. All it is a packet of water inside the envelope and some solid ammonium chloride. And when you break that packet open, it mixes the water with the ammonium chloride. It absorbs heat to do it, and it's pulling heat out of your banged up ankle to make it an endothermic reaction so it can dissolve. Now there are some exceptions to that. There are some materials that are exothermic when you dissolve them. So example, calcium chloride. If you dissolve calcium chloride, the water actually warms up, because notice the sign is negative here, which means calcium chloride is losing energy to the surroundings, okay, which would include your hand or a thermometer or something like that. Now, how am I going to put this delta H of solution to work? Well, here's a complicated example, but let's go through it. Student adds 1.01 grams of lithium bromide to 12.2 grams of water. Here's your starting temperature, 20.1. Here's your ending temperature. So this looks like a calorimeter problem. We've got a delta T, we've got a mass of water, and we know the specific heat of water. So we're going to approach this exactly like a calorimetry problem with Q equals S times M times delta T. So once again, we know the specific heat of water, we know the mass of the water, and we know the delta T. So we're just going to do Q equals S times M times delta T, and we get the Q of the water, notice, which got warmer. So this dissolution must be exothermic. The material dissolves, it gives off heat, the water warms up. Okay, so the sign on this for Q of water is positive 572 joules. Okay, now that's not what the question asks though. Note, the question asks, calculate the molar heat of solution for lithium bromide, and that's going to be in kilojoules per mole. Well, we know kilojoules, we just figured that bit out, but we don't know the number of moles of lithium bromide we have. And that's easy for you guys. Here's the mass of lithium bromide that's given to us, and here's the molar mass. You got to look that up. So we calculate the number of moles of lithium bromide, and then we can do the final calculation. Kilojoules per mole, which is what we're asked for, remember, is just a division. Number of kilojoules, there it is. okay, divided by number of moles. Now, why did I switch signs here? Why is it positive over here for the water, but negative over here for the lithium bromide? Well, think about a calorimeter, okay? The calorimeter water got warm. We saw that. That was part of the question. That means something else must be losing the energy, and it's the lithium bromide. So that is actually should be a negative 49 kilojoules per mole for that final answer. Okay, here's a more complicated one, and I'm just going to run through it, but this includes experimental data for sodium hydroxide. So we're going to measure out a mass of sodium hydroxide with a measuring paper. We're going to dissolve it in a known amount of water and then measure the temperature change. So once again, Q equals S times M times delta T. It's a calorimetry problem, okay, because water is absorbing that heat. So let's take a look at what we're going to do. We're going to do Q equals S times M times delta T first, okay? We know the specific heat of water. We know the mass of water. This is an experimental number. Just here's the foam cup, and here's the foam cup plus water. So we subtract and get the mass. Anyway, and we know the delta T. So by doing Q equals S times M times delta T, we end up with this number. This is just plug and chug. So we got 4.33 kilojoules. But once again, the question is asking, calculate delta H for the process in kilojoules per mole. So now we know kilojoules. Let me change colors of my pen. We know kilojoules. We got to figure out number of moles. And we were told, all right, it's 4.01 grams of sodium hydroxide. It's 40 grams per mole, so it's about a tenth of a mole, pardon me. So the final step is kilojoules, which we have, divided by number of moles we have, or negative 4.33 kilojoules per 0.1 mole. And notice again, the sign is negative because the water warmed up. If the water warmed up, and it did, that means the sodium hydroxide rather is losing energy in the process. So the sign must be negative. It must be exothermic. Okay, two more types of delta H. One is fiery and fun. It's the delta H of combustion. Okay, so this is the standard enthalpy of combustion for 1 mole of some kind of fuel. And remember, for combustion, the sign is always negative. Delta H is always exothermic when you're burning stuff, right? So here's an interesting table. It just shows, about 10 different fuels. And notice what's right up there in the top two. Sugar is the very top one. And second to that is gasoline. And it's curious, isn't it, that sugar actually contains more stored chemical energy per molecule than octane, a component of gasoline. Another couple things that are interesting, here's ethanol. Ethanol is used in a lot of modern car engines. It's about 10% of what you fill up your tank with. But notice, if you fill up your tank with 100% ethanol, you're going to hurt your engine because it only contains about a quarter of the calories of gasoline. So it's nowhere near as good a fuel, and it's expensive to produce. So it's maybe not the answer to eliminating fossil fuels. The other thing to note is hydrogen. We know it's explosive, but for a very light molecule, it contains an awfully high energy content. So that's why it's discussed quite a bit as a fuel. So how would I use delta H of combustion? It's just like delta H of solution. You're going to be asked a question where you're given a mass of a compound, in this case 165 grams of propane, and if you're combusting that, how much heat is released. Well, you know you're going to have to convert mass to moles, right? So let's do that first. Here's 165 grams of propane. Here's the molar mass of propane right there. So we've got 3 3/4 moles of propane. Now, how much heat is released per 1 mole of propane? Well, we need this table right here. So we got to go find propane, and there it is. Let me actually circle that in blue so you can see that a little better. It's negative 2219 kilojoules per mole. Note the units, okay? And we know the number of moles. It's 3.75. So really all you're going to do is take 3.75 moles, multiply it by the 2200 kilojoules per 1 mole, and you get the number of kilojoules released. Okay, if I were to do the same thing for hydrogen, it might look like this. Okay, 206 grams of hydrogen is combusted. Well, let's do it all in one line. You have 206 grams. We're going to convert that to moles. A mole of hydrogen, don't get Brinkelhoft, is 2.02 grams. Okay, so now we've got moles, and then we're going to multiply that by negative 286 kilojoules per mole. That's that number right here that was given to you in the problem set. So that will tell you how much heat is evolved. All right, good. Moving along. The final one are changes of state, solids to liquids and liquids to gases, or vice versa. Remember that they must include an energy state because a liquid is a higher energy state than a solid. So melting ice is endothermic. It's taking in energy. So anything going left to right, liquid to a gas, boiling off a liquid to a gas phase is also endothermic. And going right to left, in this case, would be exothermic. If I take a liquid and I cool it to a solid, it must release energy. So you got to be a little careful about the signs in these cases. So first, let's look at the endothermic ones, right? Things that are going solid to liquid. Notice up here, that's going to be going to the right. And things that are liquid to gas, they're going to the right. So the sign is positive. Now, that's delta H of fusion. Remember, fusion's a weird word for melting, but it's the chemistry word for melting. Okay, now, if I have a mole of ice and I melt it to a liquid, it's going to release a certain amount of heat. What if I have a mole of liquid water and I freeze it to ice? So this is delta H of solidification. It's the same amount of water, so the heat change is going to be exactly the same except negative, the opposite sign. Okay, so notice that there are some relationships here. The delta H of fusion is directly related to the delta H of solidification. They're just opposites, okay? And similarly, if you boil liquid to a gas, the energy change is going to be opposite. Oops, let's undo that. Is going to be opposite taking the gas and condensing it to a liquid, okay? And the reason you need to know this is because typically when you're given these values in a table, so let me show you down here, you're only given one of the two. So for example, water, we're told the delta H of vaporization from liquid to a gas. And notice that it's positive. That makes sense. We're not told the delta H of condensation, which again is the opposite of vaporization. Well, you don't need to tabulate it. It's exactly the same number. It's just a negative sign. Okay, so be a little careful of your signs again here. All right, let's see how this one works. So here's an example. 275 grams of ammonia condenses to a liquid. So this is ammonia gas. We're condensing it. It must be exothermic. How much heat is released? Convert mass to moles. Okay, that's your first step. All right, so we're going to take 275 grams of ammonia and we're going to convert it to moles. There's the molar mass. And then note the sign. It is negative. Now, where did I get this number from? Well, I got to go find a tabulated value. Right? So I go back to this and I note that the delta H of vaporization for ammonia is 23 kilojoules per mole, but it's positive if you're boiling liquid ammonia to a gas. But the question didn't ask that. The question asked, all right, what if we condense the gas to a liquid? How much heat is released? So the sign must be the opposite of that tabulated value, which was the vaporization value. So anyway, take number of moles, multiply the heat change per mole, and you get the answer. And whoa, that should be a negative sign in there. That should say negative 377 kilojoules. Okay, here's another example, which is nearly precisely the same with one twist, that how much heat is required to boil 200 milliliters of ethanol. So the problem here is that we don't have grams of methanol, but given as part of the question is the density of ethanol. And remember, density is just a conversion factor from volume to mass, okay? So we're gonna have to include one slight extra step. Convert volume to mass using density, then convert mass to moles using the molar mass of this stuff, and then multiply number of moles by the heat change, okay? And again, where'd you get that heat change value? It's gotta be tabulated. Look, 38.6 kilojoules per mole for ethanol. Let's go look and see what the table says. Yeah, 38.6 positive because we're boiling the stuff. So it is a vaporization value. Okay, back to this slide quickly, and let's just show you the calculations. Okay, so we take the 200 mils, we convert to mass by multiplying by grams per mil. So mils cross out. Let me get that. Mils cross out. Okay, now we've got grams of ethanol. Let's convert to moles of ethanol. So we multiply by the molar mass, divide by the molar mass, and then multiply that by the number of kilojoules per mole. So we've converted to moles and multiply by the heat per mole, and you get some value which is positive. Okay, that should summarize all of section 2, and good luck and ask questions next time we meet in class.